Chapter 8. Water. Water has special significance. Nearly every culture and religion includes a ritual involving water. For example, Orthodox brides traditionally were required to go to the mikveh, a water bath, before marriage. In this chapter, we will explore the uniqueness of water. A water footprint calculates the total amount of water used by a person, business, country, or the planet. The average water footprint for a US citizen is about 2,000 gallons per day. This volume used per person per year exceeds the water used to fill an Olympic-sized swimming pool. And then you may be wondering, what is the biggest contributor to a person's water footprint? This is clearly not drinking water. The drinking water only accounts for less than 0.1% of a person's water footprint. You may think that much of our water use comes from long watering, showering, and flushing the toilet. But we also must account for the water use associated with the food we eat and the products we use. For example, if we eat a piece of pork, we must consider not only the water content in the pork, but also the water content of the food eaten by the pig. We also must consider the water used to irrigate the land that was used to grow the pig's food and the water used to clean its pen. As illustrated in this example, agriculture accounts for a significant chunk of water usage. Irrigation of crops accounts for 70% of the water used in the United States, and this usage contributes to the personal water footprint of anyone who uses or consumes products made from irrigated crops. This picture on the slide shows the top 8 water-using crops in the US. The global water footprint is about 1,000 gallons per person per day. The US water footprint is about twice the global water footprint. The US and Mauritania from West Africa are the top 2 countries with the highest water footprint, according to the figure to your right. 70% of Earth's surface are covered by water. If there is so much water, then why worry so much about our water footprint? Don't we have plenty of water available on Earth? The answer is yes, we do have a lot of water on Earth, but 97% of that water is salt water, and salt water is not potable. It is not safe for human consumption. Salt water contains 3.5% salt by mass, so an 8-ounce glass of salt water contains roughly 1 teaspoon of table salt. Nobody wants to drink that. Salt water can be desalinated, but this is an expensive process. Apart from the 97% salt water, the fresh water makes up only 3% of the water on Earth, of which 68% of this exists in glaciers, ice, and snowfields. About 30% of the fresh water is underground water, and 1% is in the atmosphere. We are left with only 0.3% as fresh water on the Earth's surface. The water cycle moves water among these water reservoirs. Within this cycle, as shown in the picture below, water can exist in any of its phases: gas, liquid, or solid. Liquid water on the Earth's surface, including water in the oceans, lakes, and rivers, can undergo evaporation, a change of phase from liquid water to become water vapor. As water vapor moves upward into cooler regions of the atmosphere, it condenses. Condensation is the phase change from gas back to liquid. When water in the atmosphere returns to the Earth in forms of snow, sleet, hail, or rain, this is called precipitation. Ice caps, glaciers, and snowfields are reservoirs that hold water in the solid phase, ice. When liquid water freezes, ice result. When ice melts, it becomes liquid water. It is also possible for ice to become water vapor directly through the process called sublimation. Much of Earth's freshwater supply is polluted. The U.S. Environmental Protection Agency (EPA) defines a Superfund site as an uncontrolled or abandoned place where hazardous waste is located, possibly affecting local ecosystem or people. There are more than 1,000 locations around the country on the Superfund list. When a site receives Superfund status, this label sets into motion a series of EPA-led actions that should result in cleaning up the site over time. The Superfund division of the EPA researches the site history and identifies the parties responsible for the contamination. Those parties are then held responsible financially and legally for cleaning up the site in collaboration with the local community. The Newton Creek in New York City is an example of a Superfund site. This river becomes so polluted due to raw sewage dumped by the local residents and oil dumped by refineries along the river shore for years since the beginning of the 19th century. The picture on the left corner shows the members of the North Brooklyn Boat Club boating on the Newton Creek. The water we drink in the U.S. is carefully monitored and protected by the Safe Drinking Water Act, passed by Congress in 1974 and later updated in 1996. Regardless of the sources of the drinking water, such as lakes, reservoirs, and underground aquifers, all drinking water must be treated to make it drinkable, even if the water source is very clean. The figure on the right-hand side depicts a typical water treatment plant. Water from a natural source is pumped into the plant, where large pieces of debris is filtered out with a screen. Next, a flocculant is added. A flocculant is a compound that becomes fluffy and cloud-like when mixed with water as part of the purification process. After mixing, the flocculants are allowed to settle to the bottom of the tank, and then they take particulates in the water with them. This step removes smaller debris and particles that made it through the screen. The water is then disinfected with the chlorine molecules to kill the virus and bacteria that naturally grow in the water reservoir. After being disinfected, the water passes through layers of sand and gravel to remove any remaining particles. More chlorine may be added for disinfection, and fluoride ions also go into the water. The purified water then flows out to business and homes. Drinking water is not easy to come by in some parts of the world. Areas without water treatment plants use other methods to purify their water, like the P&G products that can be added to water to purify it. Water boils at a high temperature compared to other molecules of the same size and structure. It also can dissolve many substances. Why is water so unusual in comparison to many other molecules? To understand the answer to this question, we have to think about the interactions between molecules, which we call intermolecular forces. The intermolecular forces are different from the covalent bonds within a molecule. For example, within a water molecule, covalent bonds attach the oxygen to each of the hydrogen atoms. In contrast, intermolecular forces hold one water molecule to its neighboring water molecules. The distinction is illustrated in the picture on the left. These intermolecular forces are much weaker than the bonds that hold atoms together within a molecule. There are many types of intermolecular forces. In this chapter, we will discuss the hydrogen bonds and dipole-dipole interactions. Hydrogen bonds are the strongest type of intermolecular force. Within the covalent bond between oxygen and hydrogen in water, the electrons are not shared equally between the two atoms due to the difference in electronegativity. The oxygen atom in water pulls electron density away from the hydrogen atom, leaving it with an exposed partial positive charge. The partial positive hydrogen of one water molecule is attracted by the partial negative oxygen of another molecule. This attractive force is called a hydrogen bond. Hydrogen bonds can also exist between hydrogen and nitrogen or hydrogen and fluorine. Because each of the OH bonds in water is polar and the molecule is bent, the whole molecule is polar. The buildup of electron density around oxygen means that part of the molecule is more negative than rest of the molecule. We depict this unevenness of electrical charge called a dipole by drawing an arrow through the water molecule. The head of the arrow points to the more negative end of the molecule, and the plus sign points to the more positive end of the molecule. When molecules of water mix it with one another, the dipoles in each molecule affect how the molecules move and interact. The positive end of the dipole of one water molecule is attracted to the negative end of the other molecule's dipole. This is a dipole-dipole interaction. As shown in the figure on the left, some of the water molecules make more than one hydrogen bond. When water freezes into ice, the hydrogen bonds hold water molecules in a rigid hexagonal pattern. If we extend this structure into 3 dimensions, we get the arrangement you see in the figure on the right. Ice has a 3-dimensional crystal lattice that's based on this repeating hexagonal motif. One result of this open hexagonal lattice is that ice contains a lot of empty space. These empty spaces make ice less dense than liquid water. Density is the mass per volume of a substance. Some common units we use for density are grams per milliliter, kilograms per liter, and milligrams per milliliter. The mass of ice that can fit into a certain volume is less than the mass of water that can fit into the same volume. Therefore, we can say ice has a lower density than water. Ice density is about 0.92 grams per milliliter, and water density is about 1.00 grams per milliliter, although the density difference is only about 0.08 grams per milliliter. This makes a huge impact on our daily life. For example, in winter, the water in a lake or river freezes at the surface first. And because ice is less dense than water, that surface ice does not sink to the bottom. The layers of ice act as an insulator for the water below, allowing aquatic organisms to survive through the winter. If ice sank in water, bodies of water would freeze solid, and the world would be less habitable. Let's take a closer look at phase changes within the water cycle. Phase changes occur in pairs. For example, snow and ice can melt to become liquid water, and liquid water can freeze to make ice and snow. Pairs of phase changes like melting and freezing can go back and forth. Water easily cycles between those phases. Because the water molecule remain intact and are not changed by those processes. When the phase changes happen, what does change are the intermolecular forces between water molecules. In liquid water, for example, hydrogen bonds and the dipole-dipole interactions hold molecules loosely together in a disorganized jumble. When water becomes ice, those bonds shift and become more regular, more orderly, and better organized. The reverse happens when the ice melts. We define freezing point as the temperature at which a liquid becomes a solid. The melting point of a solid is the temperature at which the solid becomes a liquid. Those two terms, freezing and melting, describe the same temperature, but that temperature is approached from opposite directions. This concept is illustrated in the picture below. The phase changes of water are a very common experience for all of us. However, other substances change phase at temperatures different from the temperatures at which water changes phase. For example, nitrogen is a gas at room temperature. That means it must be cooled to become a liquid, and cooled even further to become a solid. Nitrogen freezes at minus 210 degrees Celsius. In contrast, gold is a solid at room temperature. It melts at 1063 degrees Celsius, which is significantly greater than room temperature. It can seem strange to think of melting and freezing as occurring at very high or very low temperatures because we are so accustomed to think of phase changes for water and not for other substances. The freezing of water contributes to hurricane formation. Cold temperatures at the top of hurricanes cause the formation of ice crystals. These accelerates the intensity of a hurricane because the formation of ice from water releases enormous amounts of heat. It is an exothermic reaction. This heat causes the air to expand, and the expansion of the air in turn causes winds to rise. Temperature stays constant during a phase change. Recall from section 8.2 that the water molecules in ice are held in their hexagonal lattice by rigid hydrogen bonds. As the temperature rises towards the melting point 0 degrees Celsius, the added heat energy makes the molecules vibrate more and more vigorously. The more the temperature goes up, the more they shiver and shake. At the melting point, however, the available heat energy used not to make the molecule vibrate more vigorously, but instead to break the hydrogen bonds between molecules. The energy that goes into the water at its melting point is used to disrupt the rigid hydrogen bonds that gives the ice its structure. In other words, all the energy absorbed is used to change the ice to liquid water, and there is no heat energy available to rise the water's temperature once the ice is completely liquefied. However, the energy that is put into the water again goes towards increasing the movement within it. The figure below shows the process of water changing phases, with the change in temperature on the y-axis and the amount of heat added on the x-axis. We call this a heating curve. At the lower left corner, where the temperature scale begins at minus 25 degrees Celsius, the temperature rises as heat is added to the ice. As the temperature of the ice increases, the molecules within it vibrate more and more vigorously. Then, when the melting point is reached, the line becomes flat. At this point, heat continues to be added, but the temperature does not increase because the added energy is used to break the rigid bonds of ice to make liquid water. When melting is complete, the temperature begins to rise again because the added heat goes towards increasing the motion and the vibration of the molecules of water. When water reaches its boiling point, the same phenomenon occurs again as it starts to change from liquid water to water vapor. The temperature stays constant until every liquid water molecule has become water vapor. Once all molecules are in the gas phase, the temperature once again starts to rise, and the water reaches the gas phase, shown at the upper right in the figure. Notice in the figure that we can consider each horizontal line from two perspectives. The horizontal line at 0 degrees Celsius represents melting if heat is being added, which means moving left to right along the horizontal axis, and freezing if heat is being removed, moving right to left along the horizontal axis. Likewise, the horizontal line at 100 degrees Celsius represents boiling, phase change from liquid to gas if heat is being added, moving left to right, and condensation, phase change from gas to liquid if heat is being removed, moving right to left. Water has a high specific heat. The specific heat of a substance is the amount of heat energy required to rise the temperature of 1 gram of a substance by 1 degree Celsius. Let's put this in context. If a certain amount of heat is added to a certain amount of water, the temperature will rise by a relatively small value. If the same amount of heat were added to most other substances of the same mass, the temperature would rise by a larger amount. We can say that water can hold a lot of heat energy. The relative high specific heat of liquid water has important consequences for our daily lives. We will see this on the next slide. The relatively high specific heat of water has important consequences for our daily lives. If you live near an ocean or a large lake, you may have noticed that the temperatures in your area tend to fluctuate much less than in places that don't have a large body of water nearby, as shown in the figure to the right. The average temperature fluctuation is defined as the average high temperature minus the average low temperature. This difference can be attributed, at least in part, to the very high specific heat of liquid water. Cities close to the water enjoy more moderate weather and maintain a more constant temperature because the nearby water absorbs and holds heat easily, and this ensures that temperatures vary less. The extraordinarily high specific heat of water also plays a role in keeping humans comfortable. Our bodies are mostly water, and so we are able to maintain a stable body temperature because the water in our bodies can absorb heat and buffer us against changes in temperature. The same principle is at work in passive solar homes, which can provide a comfortable living environment by using only sunlight as an energy source. In some passive solar homes, large tubes of water are placed in a sunny location where they can absorb large amounts of energy when the sun is up. When the sun is set, the water in the tubes releases that heat back into the house and provides warmth. The boiling point of water depends on altitude. Water boils at a lower temperature at a higher altitude. To understand how water can boil at different temperatures, we must first think about how boiling occurs. A pot of water that's becoming hotter and hotter contains water molecules that are vibrating and wiggling. The hotter the water gets, the more energetic the molecules become. As the temperature goes up, more and more of the water molecules get so animated so that they have enough energy to escape from the liquid and become water vapor. Atmospheric pressure is exerted on all objects on Earth. Water molecules can escape from the liquid phase when the pressure inside a water bubble equals to the atmospheric pressure. Recall from Chapter 6 that the atmospheric pressure decreases as increases in altitude, because the air is denser at sea level than at higher altitudes due to the force of gravity. The lower the atmospheric pressure, the less energy required for liquids to boil, the lower the boiling point, and the longer it takes to cook food. Water molecules are still the same water molecules when they move from one phase to another. They do not change composition. Each one is still made up of 2 hydrogen atoms and 1 oxygen atom, covalently bonded together in the band shape. The only thing that changes as water moves from gas phase to liquid phase to solid phase is the amount of interaction between the molecules. To summarize it, phase changes do not involve breaking or forming bonds within molecules, but they do change the intermolecular forces between molecules. Question 1. Products that come from crops such as corn, soybeans, and cotton have large water footprints. What percentage of water used in the USA is for crop irrigation? A. 10%, B. 30%, C. 50%, D. 70%. Please pause your video here. The correct answer is D. 70%. Please refer back to slide number 3 for information. Question 2. How much of the water on Earth is fresh water? A. Less than 1%, B. 3%, C. 30%, D. 97%. Please pause your video here. The correct answer is B. 3%. Please refer to slide number 6 for information. Question 3. What is the correct order of the treatment steps that occur in a typical water treatment plant? A. Settling, disinfection, flocculation, disinfection with fluoride, filtration, and screen. B. Screen, flocculation, settling, disinfection, filtration, and disinfection with fluoride. C. Disinfection with fluoride, settling, screen, flocculation, filtration, and disinfection. D. Flocculation, screen, disinfection, filtration, disinfection with fluoride, and settling. Please pause your video here. The correct answer is B. Screen, flocculation, settling, disinfection, filtration, and disinfection with fluoride. Please refer back to slide number 9 for information. Question 4. Which statement is describing intermolecular forces? A. Methane can react with oxygen to form carbon dioxide and water. B. Water molecules are formed from the covalent bonding between an oxygen atom and two hydrogen atoms. C. Water is cooled and the ice forms a hexagonal shape. D. Methane molecules have a tetrahedral shape. Please pause your video here. The correct answer is C. Water is cooled and the ice forms a hexagonal shape. The intermolecular forces are the attractive forces between molecules. B describes the intramolecular forces, that is the covalent bond formed between oxygen and hydrogen atoms. Question 5. What is a hydrogen bond? A hydrogen bond is the intermolecular attractive force between polar molecules that have a hydrogen atom bonded to either a nitrogen, oxygen, or fluorine atom. B. A hydrogen bond is the covalent bond between a hydrogen atom and a carbon atom. C. A hydrogen bond is the intermolecular attractive force between diatomic hydrogen molecules. D. A hydrogen bond is the covalent bond in polar molecules that have a hydrogen atom. Please pause your video here. The correct answer is A. A hydrogen bond is the intermolecular attractive force between polar molecules that have a hydrogen atom bonded to either a nitrogen, an oxygen, or a fluorine atom. This is a simple definition answer. Please refer back to slide number 12. Question 6. What would happen if there was a gasoline spill in a river? A. The water has a higher density and it floats on top of the gasoline. B. The gasoline has a higher density and it sinks below the water. C. The water has a lower density and it sinks below the gasoline. D. The gasoline has a lower density and it floats on top of the water. Please pause your video here. The correct answer is D. The gasoline has a lower density and it floats on top of the water. Gasoline has the density about 0.7 to 0.8 gram per milliliter. Water density is about 1 gram per milliliter. The lighter density gasoline will sit on top of the more dense water. Question 7. Based on the following information, which substance has the highest melting point temperature? Table salt is a solid at room temperature. Mercury is a liquid at room temperature. Water is a liquid at room temperature. Methane is a gas at room temperature. A. Methane. B. Mercury. C. Water. D. Table salt. Please pause your video here. The correct answer is D. Table salt. The melting point of a substance is the temperature at which it changes state from solid to liquid. If a substance is in a gas or liquid state at room temperature, its melting point should be less than the room temperature. The table salt is a solid at room temperature. As temperature rises, it will eventually turn into a liquid. Therefore, table salt has the highest melting point temperature. Question 8. What type of process occurs when an ice cube turns into liquid water? A. The ice is condensing and it is an endothermic process. B. The ice is condensing and it is an exothermic process. C. The ice is melting and it is an endothermic process. D. The ice is melting and it is an exothermic process. Please pause your video here. The correct answer is C. The ice is melting and it is an endothermic process. Condensation is the process where water vapor becomes liquid. Melting is the change of a solid into a liquid when heat is applied. Ice cubes require heat to melt down to liquid water. It is an endothermic reaction. On the other hand, exothermic refers to heat being released during a reaction. Question 9. On a heating curve, what happens when a liquid starts to turn into a gas? A. When the liquid reaches its boiling point temperature, the temperature increases steadily until all of the molecules turn into a gas. B. When the liquid reaches its boiling point temperature, the temperature stays constant until all of the molecules turn into a gas. C. When the liquid reaches its melting point temperature, the temperature increases steadily until all of the molecules turn into a gas. D. When the liquid reaches its melting point temperature, the temperature stays constant until all of the molecules turn into a gas. Please pause your video here. The correct answer is B. When the liquid reaches its boiling point temperature, the temperature stays constant until all of the molecules turn into a gas. Using water as an example, when water reaches its boiling point, it starts to change from liquid water to water vapor. The temperature stays constant until every liquid water molecule has become water vapor. This is represented by the flat line portion of the heating curve. Once all molecules are in the gas phase, the temperature once again starts to rise, and water reaches the gas phase, which is this portion, with an upward slope. Question 10. What happens when water evaporates? A. The water molecule has absorbed enough energy to overcome the hydrogen bonding intermolecular attractive forces, and the water goes through a phase change. B. The water molecules have enough energy to break the covalent bonds and a chemical reaction occurs. C. The polarity of the water molecule keeps the water molecules closely packed together. D. The net dipole of the water molecules allows the water molecules to easily overcome the ionic bonding forces of attraction. Please pause your video here. The correct answer is A. The water molecules have absorbed enough energy to overcome the hydrogen bonding intermolecular attractive forces, and the water goes through a phase change. As the temperature rises towards the boiling point 100 degrees Celsius, the added heat energy makes the molecules vibrate more and more vigorously. At the boiling point, however, the available heat energy is used not to make the molecule vibrate more vigorously, but instead to break the hydrogen bonds between molecules. Once all hydrogen bonds are broken and the water molecules vaporized, the temperature will rise again. This is a phase change of water.